Okay, Algebra 1, we're going to look at lesson 3.9. We're going to build upon solving systems of linear inequalities, and we're going to talk about some linear programming today. Sounds kind of difficult, but it's really just expanding on what we did last time as it relates to those systems of linear inequalities. And you remember when we went to solve those, we were looking for our overlap of the shading. So again, that's going to be what we're looking at, but if we read this problem, I'll just give you the basics of it here. You can read it on your own if you want to. Christian's raising money for charity. He's going to do that by mowing lawns and by raking leaves. He's going to charge $7 for raking leaves, and he's going to charge $5 for mowing lawns. It gives us some stipulations in here, though. It says each week he mows and rakes no more than 15 lawns, which means together. He's not going to do more than 15. It also says he will mow at least one lawn, and he will rake somewhere between 1 and 6 lawns. Okay, so he's at least going to mow one. He's going to at least rake one, but rake no more than 6. So as we look at this, we've set up a linear programming problem. We've got 4 different limits on us as we read through those. And we're not going to go over all those right now, but just understand that that's what we're looking at. The overlap and shading, as you can see, comes up right here. And what linear programming is going to allow us to do is look and see and optimize our return. For instance, like here, he's raising money for charity. He obviously wants to try to raise as much as possible. So he would be looking to get the maximum amount of money that he could find, or that he could get from mowing or raking. So that's what we're going to do. We're going to be looking at these constraints, a feasible region, which would be our shaded region where it overlaps. And we're going to be looking for some maximums and some minimums within those feasible regions. So just follow along here and we'll get the basics of what we need to go forward with some application problems in this linear programming lesson. So first thing we want to look at is what linear programming is here. It's a method for finding the maximum and minimum values. I like to call those the optimization values for some quantity. So this system of linear inequalities that we write in, they're called constraints. Okay, they are what are going to encapsulate this feasible region for us. So right down here we've got 4 inequalities. Okay, so you should be comfortable graphing all of these y equals a number, or y greater than or equal to a number, y less than or equal to a number. You should know that those are horizontal lines. These are in slope-intercept form, so they would be relatively easy to graph. So as we go forward here, let's just click on these and we'll show. Alright, that's a horizontal line, we're shading above it. There was a horizontal line, we were shading below it. Okay, now we've got some slope there. Alright, with that one. And here we've got some slope. So you can kind of take a look at this and look at our feasible region. Our feasible region is where everything overlaps itself. We were above this line, we were below this line. We're to the right of this line, to the left of this line. Well, you can tell that our overlap is right here in the middle. Okay, that's what we call our feasible region. Which shape would best describe that feasible region? Well, think to yourself, is it a square, a circle, a trapezoid, or a parallelogram? We should say it is a trapezoid. Alright, and here's a picture of what we would see without all the excess shading there. Alright, so that's just a little idea into what is linear programming. Okay, now let's look at another example here. Which region best describes the feasible region? So we should be able to just look at this graph. This green line we shaded above it. Now I don't have the equations or anything, I can just see. Green line we shaded above that green line. Blue line we shaded below. So the feasible region of these would be where those two overlapped, which you can tell is region 2. Alright? Okay. Now it says when the overlap of the shaded regions forms a shape, the feasible region is said to be bounded. Alright? Now that will form a shape. You'll see we had 4 there. It formed a rectangle. We have 3 constraints there. We formed a triangle. Alright. Now, there is also a feasible region which might be unbounded. Okay, you can see up here, there's no spillover. It stops. Stops going up, stops going left, stops going down, stops going right. Okay, same for this. Now this graph, we've got the red, the green, and the blue line. The green shaded left, the blue shaded below it, so my overlap is here, right? And then the red shaded below that, so my overlap is this triangle looking shape. However, there's nothing stopping it from going down, right? So as I zoom out, you know, there's no constraints on that. Let's zoom back in. Okay. Show that feasible region. It's right here. It wasn't quite a triangle shape, right? Because it flattened out right here. Plus, there's no lower limit to these. See, it just keeps going down and down and down. Okay? So that's what we refer to as being unbounded, a feasible region that's unbounded. Alright. When we talk about vertices of a feasible region, if we have a bounded feasible region, you will have vertices that fall on the constraints right here. They're pretty easy to tell what our vertices are of this shape. If it's a rectangle, obviously we're going to have 4 vertices. Okay. If it is a triangle and it's bounded, I've got 3 vertices that you can see here. So we can click on that. There we go. Now over here you'll notice we've got one that's unbounded. However, I do have 2 vertices. Right there and right there. So when I click on those, they do in fact have 2 vertices. But I don't have any vertices over here because it's unbounded. It keeps on going. Oops. Okay. We can identify these. All you have to do is pick out the X and Y values. I'm not going to plug those in. You should be able to identify those by counting over X and down a Y value. Okay. Now let's look at this last one. Consider this system of inequalities. I've got all this mess in here, right? Green I shaded down, blue it looks like I shaded below it. shaded to the left of it. Okay? Is 6, 6 a vertex of the feasible region? So what that's asking is this a vertex of the feasible region? Well, I should be able to tell from that the green graph shaded below it. But then another constraint was the blue graph shaded below it. Therefore, my feasible region should not extend up to that point right there that the cursor is on right now. Therefore, 6, 6 should not be a vertex of that feasible region. Okay? That feasible region is unbound, and it runs from right there where my cursor is now to over where it is now, and extends downward. It's unbound. Extends all the way down here. Okay? So let's move on here. Page 2. We're not going to cover all the pages. We'll cover the basics of what I feel like we need to. Now, finding the maximum and minimum values for bounded regions. Okay? Here's what we're going to look at. Okay, we're looking at those right here. You've got an objective function here. Okay? It's the function in two variables that represents the quantity to be maximized or minimized. Okay, now we'll use function notation because we are going to plug in x's and y's. So if we're given this objective function right here, it's going to show us how to do this. Click each function, or click each point, I'm sorry. Okay, when I plug that into my objective function, I get a value of 6. Okay? Now, when I plug it into a 3, 4, I get 18. Plug in -5, -4, I get a negative value. And 5, -4, I get another negative value. So it's pretty easy to tell right here that this right here would be my maximum optimization. Alright. And this one down here would be my minimum. Okay. So, we've kind of covered all that here. Now, let's use the vertices of these to look. So below, we've got our objective function right here, 4x minus y. Okay? So if I've got that objective function, I'm going to take these vertices of this triangle of our bounded region, our feasible area here, and plug it into this objective function to figure out what the maximum and minimum will be. So let's first identify the coordinates. I've got a point at 0, it looks like 0, 5. Alright, so I'll drag that one down there. Looks like I've got a point at 4, 3, or is that 2? 4, 2. And there we go. And I've got a point at -3, -2. Whoops. We'll check that. Okay, we've got those. So, now I need to evaluate that objective function at those points. So let's click on Show Me. Alright. The first point we're going to put in is 0, 5. So I put in a 0 for x, a 5 for y. That ends up being 0 minus 5, which is -5. Okay? So let's think to ourselves. Okay, we've got this objective function right here. We're going to plug in a 4, 2. If I plug in a 4 here and a 2 here, 4 times 4 would be 16. 16 minus 2 would be 14. Okay, so that's greater than that. So far, this one would be our maximum, right? Plug in a -3 and a -2. -3 times 4 is -12. Minus a -2 would be +2, which takes you back to -10. That would actually be our minimum. So 4, 2 would be our maximum. -3, -2 would be our minimum. Okay? So we don't really need to do this all that much. Okay, so hopefully you are getting the gist of this right here. There's not too much else to have to do. Your objective function will be given to you. So you'll be able to just simply plug in those vertices to figure out, if you're trying to, let's say you've got a, like that problem we had at the beginning, you're trying to maximize the amount of money that you're bringing in for charity. So if you're looking to maximize that amount of money, you would want to find all those vertices of that very first thing that we looked at and figure out, well, which one gives me the highest number. And that would be your maximum. Okay? So let's look at, let's see if we want to do anything else real quick. Oh yeah, I wanted to show this. So finding the maximum and minimum for unbounded regions. So I'm going to play this video. Turn my speaker up a little bit so you'll be able to hear it through my microphone.
To determine whether or not this objective function can be maximized or minimized for the given constraints, we will first graph each linear inequality. Y is less than or equal to 2x plus 12. Y is greater than or equal to 2x minus 2. Y is greater than or equal to -1/3 x minus 2. Now let's determine whether the unbounded feasible region of this system of linear inequalities has a minimum or maximum value for the objective function f of xy equals 6x plus 2y. We know that one of the vertices will result in the minimum or maximum value. The vertices of the feasible region are -6, 0, and 0, -2. Next, we evaluate each vertex using the objective function. Evaluate at -6, 0, and then evaluate at 0, -2. Since the feasible region is unbounded, we know that there is either a maximum or a minimum value. We see that -36 is the lesser of the two values, which means it's possibly our minimum, and -4 is the greater value, which means it's possibly our maximum. If the value of the test point is less than -36, our lowest value, then there is no minimum. If the value of the test point is greater than -4, our highest value, then there is no maximum. Let's use a test point in the feasible region such as 0, 0 to help us decide which we have. Substituting 0, 0 into the objective function results in a value of 0, which is greater than -4. Therefore, there is no maximum value and the minimum value is -36.
Okay, that was probably a little bit confusing just based on kind of hearing it verbally. Now you did get to witness it as well, so my hope is that when we come in, we'll be able to clear up any questions over this part right here. But the key is to kind of use your visual as well. You should be looking at this and realize, hey, that is going to keep extending up here. So while it won't always be ideal to use the visual, sometimes you can take a look at it and use some common sense and realize, hey, I think this is going to have a minimum, but if it keeps extending up and up and up in a positive fashion, then, and that is where it is unbounded, then I kind of think to myself, well, I'm not really expecting to have a maximum. And then just let your numbers work from there. Okay? So we'll get together next time in class and clear up any questions over this, work on some problems, and get done. So you have a good day. Bye-bye.